Hello everyone, I'm recording this presentation as my final class presentation for the CSCE883, the machine learning course. So as I've explained in my proposal, my aim for this project was to explore the cross-modality transfer learning. What I wanted to do was to build from the scratch a flood dataset with the satellite data and then fine-tune a newly published geospatial foundation model, which is called Prithvi, and then compare its performance against UNet network to see how they would perform on a very small flood dataset. So my hypothesis for this project was that if we have a model that is pre-trained on optical imagery, by optical imagery I mean an image with at least 3 RGB channels, and also the satellite optical imagery usually has three more spectral bands as well, which are shortwave infrared 1 and 2 and near infrared. So I want to investigate if we have a model pre-trained on that kind of data can leverage the learned features to enhance its performance when we use it on a SAR imagery dataset. SAR images are usually one band images, which is basically a different thing from the optical images. And here in the image you can see it is actually the architecture for the model that I'm investigating. It's the architecture for the Prithvi model. And what I'm doing here in this project in one part is to extract the encoder and keep the pre-training weights on that, and to put another decoder on that so that I can fine-tune it and then kind of test it on a different type of dataset, which was SAR dataset as I explored architecture. So moving on, here I had two different phases. The first one, which is the most important kind of part for all machine learning projects, was to have a dataset. In this project, I had to build my dataset from the scratch. So what I did was follow this framework that I have put on the left, step by step, and then I'm gonna explain it and go through it fast. So first, I had to find flood events. I examined two different cases. One of them was Valencia flood, which happened in late October 2024, and there were like more than 220 people lost their lives due to that flood, unfortunately. And the second one was the Mississippi flood, which happened at May 2019, and it took more than a month with a lot of damages. So the second part was to get before and after SAR images of the flood. Here we can see the Valencia flood on the right hand side. We can see the images of different times, the optical images on the top and the SAR images in the bottom. As we can see, if we want to compare before and after flood, the black parts, the darker parts in SAR image kind of represents the water or the flooded area, and we can see that in the after flood we have more black areas. So those parts are the part that flood has covered. And then I have used a thresholding method by United Nations SPIDER to extract the flood mask from this comparison. This is the second flood case that I have investigated. This is the Mississippi flood. Again, you can see the different time optical images on the top and the SAR images in the bottom. The next part was applying necessary filters. So when I access the satellite imagery, I need to apply different filters to get exactly the images that I want, and nothing more than that. The first one is the temporal image. So I give a period before the flood happens and a time period after the flood happens, and I ask Google Earth Engine, which is the platform that I use to kind of interact with the satellites to get their data. I these two date periods to Google Earth Engine, and it will give me the data only in that period. The next one was the spatial filter. I need only data around the area that I want. For example, for the Valencia flood, I want it only along the Valencia coast in Spain. And in the Mississippi flood, I only want the data along the Mississippi River. So this is the second filter that I applied. The third, fourth, fifth, and sixth are the instrument mode that I have to define we usually use IW mode for flood detection tasks. Then the polarization filters, which can be vertical, 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 horizontal, 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 and horizontal, vertical. Here I had the data only vertical, vertical polarization mode, so I use that one. Then I have to choose the orbit pass filter as well as the resolution filter, which I use 10-meter resolution. It is the finest resolution that we have for the SAR images. Then I had to define a threshold and obtain a flood mask. So what I did was comparing before and after flood images for each pixel, and then I said if the difference between them is more than 20%, identify that part as a flooded pixel. It's a common practice and suggested by, as I said, United Nations Spider Framework for Flood Detection. So far I have images of the flood and initial flood mask, and I need to remove the high slopes and permanent water layers from the flood mask. So there are areas that are like the ocean or the rivers that are always water in it. So we need to remove those parts from the flood mask, because those are the parts that we have water all during the year, and these are not the parts that are flooded. So in this part I have removed those. The next step was exporting the images that I had from the Google Earth engine. Again, I exported an image from before the flood, an image after the flood, a flood mask, and a layer for the permanent water. The next issue that I faced with was the NaN values in the SAR images. So I developed a Python code to remove the NaN values. Well, not remove, but I made an interpolation, and how I managed it was to make an interpolation of the pixels around the NaN pixels and assign a value to that, which is the average of the value for the pixels surrounding that. So the the images that I have exported from Google Earth Engine are super large images. Each of them are like around between 600 megabytes to 1 gigabyte. At this point, in order to feed them into a network and train something on them, I need to kind of cut them in small and make small chips. So again, I developed a Python code to cut these GeoTIFF images into the small chips. And what I did was to build a two-band images. One band represents the before flood event, the second band represents the after flood event. And the images that I built here in the dataset are 256 to 256 pixels. Then, since the non-flooded area is much more than the flooded area, it made an imbalance in my dataset, and it didn't let my model to learn anything. So what I did was to remove the areas in which we have more than 10% unflooded area, or vice versa. I removed the chips in which we have less than 10% flooded area. Then I structured my dataset as you can see here. So I have one folder for annotations, which are flood masks, and one folder for the images, which are, again, as I explained, two-band images of before and after flood. I have divided them into test, train, and validation with the 60, 20, 20% each. Here are the images again in high resolution. Again, here, as you can see, the left one is before flood, the right one is after flood. You can see the black parts are the flooded area, and the right one, the red parts, are the flood mask. Again, for the Mississippi River is the same. So the flood data set that I created was a result of studying 4 different floods. I chose 2 of them. I made more than 250 flood image chips of 2 bands. The size of them are 256 to 256. The same for flood mask chips and permanent water layer. Well, I didn't use permanent water layer project. And on the left hand side, you can see one image, but in two different bands. As we can see, the black areas are increased. Those parts are actually the flooded areas. And in the image in the right, we can see the flood mask that I have overlapped with that image. moving on with the second phase, so I downloaded the PrithVideo Special Foundation model. I extracted the encoder part. I decoder for a segmentation task, and I trained it for to a small flood dataset that I have. To give you a small background for this kind of tasks, the flood datasets have more than 2,000-3,000 of images, but my task was actually testing if this transferability can be done of the optical images to the SAR images. So I designed a very small flood dataset. So I expect not a very high, let's say, accuracy and evaluation metrics. Here you can see on the left hand side the output of my codes. Then the next step was downloading a unit model. Again, I had to modify the decoder head a little bit to make it kind of available to work with my own data set that I have built. And you can see the training and validation loss on the bottom, which both of them are decreasing. So it shows that my model is learning across the 30 epochs. Then in order to compare the results, I have here the mean intersection over union. We can see that the Prithvi model shown with the green color has much higher mean intersection over union comparing with the unit. The reason for this is exactly the features that was learned by Prithvi model on the optical data is transferred when we want to use a totally different type of data, which are SAR data here. So this was my presentation for this course, and all the codes and results that I have made are available on my GitHub, which I will put on the email to Dr. Who, and my flood dataset that I have built is also available on my Google Drive, for which I will provide a link accompanying this presentation. Thank you all, and that was it. So what I concluded from this was that the hypothesis was correct, and then for the future works, I'm planning to build a larger flood dataset and then also add a segformer model to the dataset so that I will strengthen my argument. Then I would prepare the manuscript for the paper, and hopefully I will be able to publish it sometime within 2 months, pretty soon.